Okay, so after all this talk about mean, standard deviation and everything, we are back to the question, how long does it take for me to bike from home to London in January? I kind of answered that already, as we saw, but the truth is that uh, for you guys, you have to, I mean, the way that you answer such a question, when it comes to your thesis, when it comes to the actual scientific work that you're going to do, the methods to arrive to the answer is a little bit more intricate than that, right? The basic tools you have, the basic tools that you need in order to answer this question are the mean and the standard deviation and the data that you gathered. But there are some things that we must consider when it comes to actually designing quantitative studies. What kinds of studies you can design and which one you should choose for answering your research question, because the study is a method for answering a research question. So the type of study that you're going to use is dependent on the question that you have. So you must be able to identify it. Right? And of course, this is just a very simple question. But in this case, again, we're going to come back to that duality between sample versus population, which we discussed before. Every interesting research question that is complex enough is actually a question about a population of interest, right? And you can never, I mean, if your question is interesting enough, you can never really answer it by looking at the entire population, because the entire population is beyond your reach. So all the points that you would have to measure ever in order to have a final result or a final answer to your question are beyond your reach. So you always need to take a sample of that. And again, this is just a repetition of what we've seen before, but this is what defines statistical inference. So whenever you hear the term statistical inference, it means that you're trying to infer values from the population of interest by looking at the values from the sample. Because the sample is in your reach, but the population of interest is not. So you really don't have a choice. The only choice you have is to take a sample, measure that sample, and then statistically infer what are the values of the population of interest. Okay. And we've talked about like how representative the sample has to be and so on. But the most important part here that we're going to discuss in a bit more details now, which is something that we've already talked about, but again, I'm going to come back to it and I'm going to kind of explore each of these things in a few more details. And again, are these three very general kinds of studies that you could do in order to perform research, which will depend on what is your research question and what kind of information you're trying to obtain. From your left to your right, the complexity increases, right? So if you start with the simplest one, the simplest possible study is the sample study. Then the observational study is a little bit more complicated, and then the experiment is significantly more complicated to perform. And again, I would like to recommend this reference of Khan Academy's Statistics and Probability course, which is really good. If you like this and if you think you need to know a little bit more about this, by all means, go for it because it's really good. And the simplest, the least complex is the sample study. As we call it sample study, some people will call it one sample study. Some people will say one sample testing. But what matters is that you're performing a study by analyzing one sample, one single sample. Right? So you've gathered one single set of data of measurements, and that is what you're going to use in order to perform your study. And of course, by being just a single sample of data, and by being, of course, not part of an experiment, then the types of conclusions that you can gather from this one sample study are quite limited. You can conclude some things about it, but you need to be aware of the fact that this is the simplest possible kind of study. So there are limitations to how much information you can actually infer from the population by just doing that. Okay. The overall pipeline, we've discussed it before. I'm going to go quickly over it. Is to come up with an idea or hypothesis about the population of interest. So you have an hypothesis. I think that the value that I want to measure is X. That's my hypothesis. The hypothesis can come from anywhere. It can come from a magazine, it can come from a paper, it can come from someone who told you this. You've heard it before and you don't think that's true, or you have reason to believe it's not true, so you want to test it. Anyway, this comes from somewhere. You have a hypothesis. It's an idea about a value of a factor in a population. So someone tells you, you know what, computer science lecturers in LNU, their salary is about like 25,000 Swedish krona. Someone told you that. And for some reason, you doubt that that's true. So then you can do a study to try to verify. And then you sample your population of interest, right? You go and you take some data points from this population, always trying to have a representative random samples whenever possible. The more random they are, the more representative they are, the better will be your answer. The closest to reality will be your answer. Then you take this sample, you kind of consider this sample as being a representative sample of the population, as a mini population, and then you measure it. You measure the sample you obtain regarding your idea hypothesis. So if you sample some computer science lecturers, for example, then you ask them, what's your salary? Okay, they will tell you salary, and then you took the values of the sample, right? So you measure them regarding your idea, right, of course. And at the last step, you infer the value of the population from the sample. So it's very important to understand that this last step is always involved. There's always some error involved here. We're making an inference. We don't know if the actual population value is related or not to the value that we've just measured. Maybe the sample we measured is not representative, so the inference will not be very good. There's always error involved. Statistical inference is always about errors. And the errors are the most important part, actually, of statistical inference, to know how to understand and to study these errors. And then we infer the population from the sample, right? But like I said, there's always errors. But one question that usually comes up with people when they're starting to take a step into statistical inference is to think, well, how can we infer the population mean from the sample mean? I mean, the sample is much smaller than the population. Let's say the population has, I don't know, hundreds of thousands of individuals. And that's why it's so hard for me to reach it. That's why it's so beyond my reach, because there's too many elements in this, right? So how can you just tell me that a sample mean, for example, let's say I take the sample mean and then I infer the population mean. How can that be valid? How can I know that that's valid? You know, why can I do this if I'm inferring a value of a huge population from a small one? There is no guarantee that they match, right? Well, actually, you would be wrong if you assume that. And the reason is because the sample mean is a good estimate of the population mean. So you can indeed use it directly. And there are mathematical theories behind this that I will not go into details. I will try to offer you an intuition about it. But suffice to say that it has been mathematically studied for a long time, decades and decades and decades of people studying statistics in order to determine that, yes, the sample mean actually is a very good estimate of the population mean. Of course, the larger your sample, the better. The more points you sample, the better will be your estimate. But even smaller samples sometimes have good estimates of the population mean. And in the next lecture, I will tell you exactly how you can estimate the error that's involved in this inference, right? I'm not talking about anymore about the standard deviation of the data set. Standard deviation of the data set is a measure of how far are the points from the mean, right? So it's like a measure of the error of the mean regarding the data set itself, regarding the sample itself. How wrong is the mean when representing the sample itself? There are other methods to determine what's the error when you're using the sample mean to infer the population mean. It's another error. It's based on the sample, on the standard deviation actually, but it's another one. I actually call it the standard error, just so you know. But indeed, the sample mean is our best guess upon the population mean. It's the best thing you can have. And mathematically speaking, it is actually very good. So you can expect it to be very good. And even if it wasn't, then we wouldn't have any other tool to perform any kind of inference, right? We need it. I mean, it has to be, and it actually is. So people have proved that. But why is that so? Like, how come? How come we can actually assume that? Well, it's because there is something called a sampling distribution, which is again something that I will touch back on the next lecture. But for now, just know that the sampling distribution exists, and it is approximately normal. We've talked about normal distributions. We know how normal distribution looks like. It's like a bell. And like I said before, since we've seen so many normal distributions in real life, since the normal distribution is so heavily studied, then we know how the normal distribution behaves. So if you measure a data set and it looks normal, then you can assume all kinds of things about it because you know that normal distributions behave in similar ways. So this thing called the sampling distribution, it is approximately normal. And since it is approximately normal, we can make assumptions about it. And one of the assumptions is that the mean is very representative of the distribution as a whole. So what is the sampling distribution? Very quickly, very intuitively, I will come back to this next lecture. If I took many samples of many samples of the same size, I know how their means would be distributed. They would be normally distributed around the population mean. What does that mean? Suppose you go out and you took a sample of 30 people, right? And you did some research, and there was a mean. Now, suppose you go out and you took another sample of 30 people, and then another, and then another, and then another, and then every time you took a new mean. Those means that you took, they would be normally distributed around the population mean. I won't go into details now because I will come back to this. Just know that we have a good way to, we have good reason to believe that the sample mean that you took, that one sample mean that you just computed, it belongs in a normal distribution. And that normal distribution is a normal distribution around the mean. So we know that 95%, for example, of them are within 2 standard deviations of that mean. But anyway, I will come back to this and I will talk about this in detail, so don't worry about too much. Just understand that there is this thing called the sampling distribution. It is approximately normal, and that is what guarantees us that the mean of a sample is a good estimate of the population. Another thing that is, so you could think, well, so we do the same for the standard deviation, right? If the mean is a good estimate of the population, if the sample mean is a good estimate of the population mean, then the sample standard deviation must also be a good estimate of the population standard deviation, right? So I can assume that the population has the same standard deviation or a similar standard deviation than the one that I've just measured, right? Wrong. It's always wrong, all right? Whether you think you're right, you're wrong, and when you think you're wrong, you're also wrong. So this is also wrong because the formula we saw earlier, that was for the population standard deviation. That was like if I wanted to compute the standard deviation, if I had all the points. But that does not work with sample values. So if I have a sample and I compute the standard deviation and I want to make assumptions about the population standard deviation, based on the sample standard deviation, we need to adapt it like we need to divide by n minus 1 instead of dividing by n, as was the fact before. Before we divided this by n, It's the same computation but divided by n, which is the number of points you have in your population. But the sample, actually, we call it S, not sigma. Sigma is reserved for population. And for sample, we just call it S. So the S is almost the same, but instead of dividing by n, you divide it by n minus 1. This is a good estimate, or the best possible estimate that we have for the population standard deviation based on the data that you have in the sample. So this is, again, something that you will see in spreadsheets and so on, but sometimes you will see that, well, actually all the time, you will see that there's going to be some option to determine whether you want the population standard deviation or the sample standard deviation. And if you have a sample, then you should use the sample standard deviation, which is this one. All right. It's a much better estimate of the population standard deviation than the actual the other one, well, when you divide it by n. And again, we're going to go into details about exactly why this is so, but this simulation here on Khan Academy, if you want to go there, you can look at it. You will see that there is a simulation that compares the two of them, and then you can see that they are indeed, this one actually is much better at